Section. Introduction. We're here to talk about a revolution in the field of natural language processing, NLP, brought about by large language models, LLMs. These models, made up of tens or hundreds of billions of parameters, have been trained on vast amounts of data using self-supervised training objectives. A prime example of this is ChatGPT, an AI chatbot that has gained significant attention. Following this, other large-scale language models like Llama, Llama 2, and PaLM have been developed, showing impressive results in language understanding and text generation. However, there are still some complex issues to tackle, such as arithmetic, common sense, and symbolic reasoning. To improve ILM's performance on various tasks, the Chain of Thoughts (CoT) series of work was proposed. This approach guides the model to generate its own reasoning steps or rationales. However, this improvement comes with the cost of generating additional rationales, which might be seen as a drawback since the main focus is often on getting the answers. Moreover, most top-tier causal transformers are auto-regressive, meaning they predict tokens one at a time, which can be slow and may not fully utilize the capabilities of GPUs. This can be a limitation for real-world applications, especially those that involve large amounts of data and require high throughput. So, we asked ourselves, can a large language model benefit from its inner approximate reasoning rationale, similar to how people usually think a lot before writing down on paper? We believe that in many reasoning tasks, a complete rationale may not be necessary. Instead, having some keywords or key information can be enough to guide the LLM in obtaining the correct answer. To test our theory, we conducted an experiment using the standard chain of thoughts task on 3 commonly used reasoning datasets. We introduced a certain ratio of placeholder tokens to replace the original tokens in the rationale. We repeated this process using 40 different random number seeds to generate variations of the corrupted rationale for the same question. We then combined the original prompt with the corrupted rationale and used it as the input for the same LLM to obtain the answer guided by the corrupted rationale. Our results showed that even a randomly sampled oracle rationale can lead to correct answers, indicating that the LLMs can make accurate predictions without having access to the complete rationale. We also found that revealing a small portion of the rationale can already result in saturated accuracy, especially for common sense reasoning tasks. Motivated by these findings, we propose a method called FastCoT. This method combines the exact tokens obtained through auto-regressive decoding with the future approximate tokens obtained through parallel decoding. By doing so, we can obtain the answer to the original reasoning task with fewer forward inferences of the large language models. Our contributions can be summarized in 3 main aspects. 1. We introduce parallel decoding into the reasoning task, such as CoT, and propose to use the byproducts of parallel decoding, which are approximate tokens, as a glimpse of the future for LLM in the decoding reasoning process. We demonstrate and analyze how parallel decoding reduces time overhead in reasoning task scenarios from 2 aspects. The first aspect comes from parallel decoding itself. Compared with auto-regressive decoding, it can reduce the number of iterations by guessing hits. The second aspect comes from glimpses into the future through approximate tokens, which can help LLM analyze the final answer in advance without auto-regressively decoding it. 2. We perform extensive experiments with different transformer sizes, base and large, and datasets, showing speedups of up to 20% in inference time. To the best of our knowledge, this is one of the first studies to introduce a speedup in the CoT reasoning task using large language models. 3. We have designed a parallel decoding framework that supports batch processing and KV cache. In the reasoning task scenario, we analyze the time overhead of each part compared to auto-regressive decoding. In terms of related work, the chain of thought (CoT) prompting was proposed to induce large-scale language models to think step by step, similar to how humans approach complex questions. After that, several methods have been proposed to enhance the performance of CoT prompting across various domains and tasks. Our work is unrelated to these engineering efforts and can be applied to any prompting method related to XOT. In terms of utilizing rationale in XOT prompting, several works attempt to use CoT-generated rationale to improve the task performance of student models across diverse datasets through rationale distillation. To the best of our knowledge, we are the first to propose exploiting the concept of approximate rationale to expedite the completion of XOT series tasks. Many works have proposed various methods for accelerating the generation of autoregressive causal language models. However, most of these methods are limited to specific domains or require careful parameter tuning. In contrast, our framework does not require any additional training on either the base pre-trained language model or a new model. To the best of our knowledge, we are the first paper to attempt utilizing these approximate tokens. Section Summary. The introduction discusses the revolution in the NLP field brought about by large language models, LLMs, like ChatGPT. However, challenges such as arithmetic, common sense, and symbolic reasoning remain unresolved. The paper proposes a method called FastCoT that combines auto-regressive decoding with parallel decoding to reduce inference time in reasoning tasks. The authors also highlight related work on CoT prompting and faster auto-regressive inference, but their framework is the first to leverage approximate tokens generated during parallel decoding. Section. Preliminary. Let's break down the complex concepts in this paper into simpler terms. The paper begins by discussing the CoT prompt, which is the initial text that guides a language model, LLM, to generate more accurate responses. This prompt usually includes a few examples with corresponding explanations and answers to the questions. Then, a task question is added that requires the LLM to reason. The CoT prompt can be created using various methods, but the specific method used doesn't affect our approach. Next, the paper talks about parallel decoding. In simple terms, when a trained model is given a prompt, it generates a distribution for the next token based on the prompt and the tokens generated so far. If we were to use a common approach without considering any post-log its processor, the next token would be selected by choosing the token with the highest probability from the distribution. However, parallel decoding is different. It considers additional tokens after the generating position, which increases the number of outputs. The paper refers to these additional tokens as the context window, and the size of the window is denoted as C. The variable t is used to differentiate the results produced by each iteration. This decoding process can be performed simultaneously with auto-regressive decoding in the LLM's forward inference. The paper then discusses a single inference task conducted to measure the time overhead for a single forward inference under different window sizes. The results showed that increasing the window size within a certain range has only a minimal impact on time consumption. However, this glimpse into the future could play a crucial role in enabling faster answer generation in XOT series scenarios. The paper then introduces the important components of the proposed algorithm. The first component is the vague rationale tokens buffer. Unlike tokens generated by large language models in typical scenarios, vague rationale tokens are not produced through auto-regressive decoding. Instead, they are obtained through both parallel decoding and auto-regressive decoding. However, these tokens are not precise for the language model's generation. We refer to them as approximate tokens. The next component is the answer trigger. This is a specific prompt that explicitly instructs the LLM to output the answer to the question. This trigger helps guide the LLM to generate the desired answer output. The final component is the answer probe. This is necessary to determine when the iteration can be terminated. This probe collects attention weights for the approximate tokens within the context window during the forward inference. These attention weight data exhibit distinct characteristics that can help determine whether it is appropriate to end the iteration. Section Summary. The CoT prompt is a text that guides the language model, LLM, to generate accurate answers by providing examples, rationales, and a task question. Parallel decoding is a process that considers additional tokens after the generating position, resulting in more outputs. Increasing the window size within a certain range has minimal impact on time consumption, but it provides a glimpse into the future that enables faster answer generation. Our proposed algorithm includes a vague rationale tokens buffer, approximate tokens obtained through parallel decoding, an answer trigger prompt, and an answer probe to determine when the iteration can be terminated. Section. Approximate rationale generation. Let's delve into how parallel decoding creates approximate rationales that aid in reasoning tasks. We'll break down the explanation into three parts: iterative inference, verification, and update. In the iterative inference stage, auto-regressive decoding and approximate decoding happen simultaneously within a single transformer call. This allows for predictions for all tokens within the context window to be made at the same time, thanks to the causal attention mask used in causal language models. During the verification stage, we contrast parallel decoding with auto-regressive decoding. While auto-regressive decoding generates only one exact token at each inference step, parallel decoding can generate more at once. We need to identify the last exact token within the vague rationale tokens buffer. This index represents the position up to which the tokens can be considered as exact, with any tokens beyond that index being approximate. We'll show various metrics to demonstrate the high quality of the approximate tokens generated by parallel decoding. These metrics will prove that the approximate tokens contain important information and contribute to the reasoning task. In the update stage, we update all the results obtained in this iteration's forward inference to the vague rationale buffer. The tokens included in the index plus a constant would be accepted as the verified exact token solution, while the excluded tokens remain as approximate tokens. These approximate tokens will enter the next iteration's forward inference as iterative solutions or serve as the vague rationale for the final answer. We've designed 3 different iteration termination conditions to determine when to stop under various circumstances. The iteration will end once any of these conditions is met. The first condition is based on the attention weight collected by the answer probe. The second condition calculates the minimum number of iterations required to achieve a certain performance loss threshold, and uses this value as the upper bound for iterations. The third condition, EOS, end of string, indicates the end of text generation and is applicable to relatively simple problems. Due to the existence of parallel decoding, the progress of text generation in the same batch may vary. We use 2 types of padding to handle this. The first type is for processing the past KV cache, which reduces the time complexity of auto-regressive decoding. The second type of padding is used when there is an instance in a batch whose next iteration's context window is not completely filled with approximate tokens. We tested our methods using 3 widely used datasets for reasoning tasks. The performance is measured in terms of acceleration, both in wall clock time and iterations saved, compared to auto-regressive decoding. We also set the repetition underscore penalty parameter to 1.2 to mitigate the issue of the model repeatedly generating the same text segment. To answer our research questions, we designed the following baseline and experiments: vanilla CoT, using the auto-regressive decoding method; truncated CoT, auto-regressive decoding but truncate generated rationale to iteration number; FastCoT, CW equals K, with O skip; and FastCoT, CW equals K, with skip. Section Summary. In this section, the authors explain the process of approximate rationale generation using parallel decoding. They describe how auto-regressive decoding and approximate decoding are performed simultaneously, allowing for the generation of multiple tokens at once. They also discuss the verification process to determine the boundary between exact and approximate tokens, and the update of results obtained during forward inference. The section further explains the iteration stop conditions and implementation details such as padding methods. Finally, the authors outline the experimental settings and comparison methods used to evaluate the performance of FastCoT in reasoning tasks. Section. Main results. We've conducted a comprehensive comparison of truncated CoT by truncating it in each iteration and performing downstream CoT task experiments with an additional answer trigger. The results of these experiments are illustrated in a figure. We've noticed that FastCoT, which has more approximate tokens than truncated CoT, performs differently in various tasks. In tasks like strategy QA and CSQA, FastCoT tends to perform better due to the presence of approximate tokens. However, in the Aqua dataset, which involves mathematical reasoning, FastCoT falls behind truncated CoT. This is because identifying useful tokens in mathematical reasoning tasks is more challenging for the language model. If incorrect data is included in the approximate tokens, it can lead to incorrect final answers. Therefore, approximate rationales are more effective in tasks involving common sense reasoning rather than mathematical reasoning. We also conducted time overhead measurements on our method and the vanilla CoT by randomly selecting 40 questions from the strategy QA dataset. The results are displayed in a table. We found that our method adds almost no additional overhead, but allows us to get the corresponding logits at the approximate tokens and the chance to save iteration cycles, reducing the infer time by almost 20%. However, calculating the approximate token in the context window after inference takes 3 seconds more than AR decoding without this step, accounting for about 10% of the GPU time. We also examined the impact of the length of the parallel decoding context window on the performance of the reasoning task. We found that as the length of the context window increases from 0 to 20, the early performance gradually improves. However, when the context window length exceeds 20, the performance does not improve but decreases. This is because the probability of parallel decoding a token that is helpful to the problem at a farther position is very low, and may even solve a token that has a negative effect. In another experiment, we used the Llama 2 model and introduced some new metrics to evaluate the quality of the approximate tokens in each iteration's context window. These metrics include first hit, total occur, PD*, AD, and total occur, AD, PD*. For methods that aim to utilize parallel decoding for acceleration, the metrics that are of greater concern are first hit and total hit. However, these metrics tend to be relatively low compared to the occurs metrics, indicating that while parallel decoding may offer acceleration benefits, these advantages may not be significant solely in terms of speed improvement. When answering based on the rationale within the approximate window, more attention is paid to the occurs metrics. This is because the reasoning step for answering the COT can be considered to be comprised of keywords to some extent. As long as these key tokens appear, they can assist the model in getting closer to the correct results, regardless of their exact position. Therefore, it can be inferred that the scenario that focuses on the occurs side indicators is more suitable for parallel decoding than the scenario that focuses on the hit side.